Hello, everyone, and welcome to today's webinar entitled 5 Tips for Large Assembly Performance, brought to us by Siemens Digital Industries Software. I'm Jim Anderton, Director of Content for Multimedia here at engineering.com, and joining me today will be Ben Weisenberger, Senior Application Engineer, Solid Edge Global Technical Enablement with Siemens Digital Industries Software. This is going to be a very exciting hour. I'm looking forward to this. There's a lot of technology to talk about. We'll both be presenting, and let's begin. Just a bit of housekeeping to start off. Today's webinar, well, it'll be recorded and it's going to be available for on-demand replay on engineering.com. For attendees attending our entire live session, well, you'll receive a PDH certificate within 48 hours of this broadcast. We also have a question and answer section at the end of the presentations, and if you have them, please submit them directly to that webinar interface in front of you. We'll try to address all questions during the question and answer. I'll pose them to Ben, and Ben will respond, so simply type them into the console at any point during the presentations, and we'll address them at the end. All right, let's begin. Today's webinar will have 2 presentations. I'm going to talk about some of the current issues in large assembly engineering facing designers today, and Ben is going to present on those 5 useful tips that you can use today to optimize your large assembly design process. Then we'll have the question and answer session. So let's begin. Now, we study many aspects of design and manufacturing here at engineering.com, and for today I've chosen just 3 out of those many factors driving change in large assembly engineering today. And those 3 I've chosen are the impact of COVID-19, of course, the effect of new manufacturing technologies, and some changes to the way we work from mass collaboration.
There's no way to talk about an important industry like large assembly engineering without looking at the effect of COVID-19 and the industry outlook as a whole. So let's take a quick look now and then take a deeper dive into the hardcore engineering. While COVID continues to spread as of right now, 2 vaccines have shown high levels of effectiveness with the production capacity to create hundreds of millions of doses by the second half of 2021. We believe that this, combined with current efforts to contain the spread, suggests that the pandemic will ease in 2021 with a V-shaped recovery in the consumer goods and services sector, which is good news for the auto, aerospace, and consumer durables industries. Similarly, the Fed has signaled that interest rates will remain flat and near zero for the foreseeable future, which bodes well for infrastructure, civil engineering, consumer goods, aerospace, and the auto sector. While we're seeing definite movement towards clean energy as a growth driver, the transition will require large assembly engineering in both conventional and carbon neutral sources. Oil and natural gas production and the need for pipelines and infrastructure are in play, and pressure on the European Union to purchase bulk LNG in preference to piped Russian gas may create a bigger global market for these specialized bulk carriers. If Washington returns to the Paris Accords on greenhouse gas emissions, we expect government support for alternate energy project spending, primarily wind turbines and grid-scale solar with battery storage. Aerospace will be unaffected by CO2 emissions limits as the industry already engineers for maximum efficiency, but in the auto sector, carbon taxes and retail price support for electric vehicles may accelerate the switch to EVs, pulling forward major automakers' platform redesign timelines and driving a ripple effect through the Tier 1 and Tier 2 supplier communities. Even without carbon taxes, internal combustion engines are going to get smaller, and plug-in hybrids and pure EVs will replace current products to meet tougher corporate average fuel economy standards and CO2 limits. 70% of the economy is driven by consumption, and the Fed has signaled that interest rates will be held to effectively zero rates for the foreseeable future. As employment rebounds post-COVID, this bodes well for autos and consumer durables. And needed infrastructure spending enjoys broad bipartisan support on the Hill. Either way, it's a positive outlook for engineers working with large assemblies.
Okay, should we really worry about the effect of COVID-19 on a macro scale? Well, in terms of the economic outlook, I'll show just this one chart before we dive into the hardcore engineering. But this is an important one. This is from the Organization of Economic Cooperation Development's Business Confidence Index for 2008 through October 2020. Now, the individual lines, they represent the major industrial economies of the world, and the black line showing the mean. Now, this is based on surveys of executives in multiple industries involved with industrial production, orders, and finished goods inventory levels. Any number over 100 represents confidence in future growth. Numbers below 100 represent pessimism toward future performance. Now, the key takeaway here is that COVID-induced recession, well, it's been short and sharp, and it's significantly less serious than the 2008-2009 downturn on the left. Now, reversion to the mean, of course, that's our friend in engineering, QA, and in economics. And in this case, business confidence at the right edge of the graph is already back up to the statistical mean, and it's well within the 1 sigma line that would suggest future growth. Now, we're seeing confirmation of this in the engineering sector, where supply chain induced production interruptions in auto and the consumer goods sector are already starting to clear. While aerospace production rates, well, they're down, but they're reflecting deferred deliveries more than outright cancellations. And we see no evidence that engineering product development has been deferred or delayed in major manufacturing sectors. If it's on the drawing board now, it's still moving forward. Now, COVID-19 is having a serious and sometimes tragic effect on individuals, but in engineering, and especially industries that work with large assemblies, we believe that the worst is already behind us. All right, let's talk about new technologies and part consolidation and increased complexity. Now, we know that simpler, it's always been better in engineering, and as production design technologies improved, most industries are actively pursuing part consolidation as a key strategy for lower cost or more reliable assemblies. Now, working against this, of course, is an increasing level of complexity driven by software control of formerly mechanical systems. Here's a typical example in fly-by-wire aircraft control systems. And there are similar emerging systems in the automotive sector. But the idea is to simplify the network of hydraulics, pneumatics, and mechanical linkages that we usually constrain mechanical engineering. But in doing so, we've in effect moved the complexity of the mechanical engineering systems to that systems engineering community on the software side. Now, the ultimate example of this, of course, is currently the Boeing 737 MAX, just FAA approved today, or FAA approved today for flight, by the way, where proven code in the form of flight control laws, where they're defeated by erroneous inputs from a defective angle of attack sensor, as pictured in the middle. Now, there's an interesting contrast here because there was a previous safety issue with the 737 about 30 years ago. And that was caused by a design flaw in a hydraulic actuator. That's pictured on the right, a purely mechanical system designed to deflect the rudder. Now, in the modern case, right now, the FAA has approved that fix for the maneuvering control augmentation system issue on the new MAX. But the overall engineering point is that making mechanical systems simpler by pushing the complexity onto the systems engineering team isn't generally a guarantee of a more robust overall system. Mechanical engineering, it still matters. New manufacturing technologies, well, they're just emerging all the time. And of course, we follow them closely here at engineering.com. And two which have a direct impact on engineering as we're talking about it here, and large assemblies in particular, are the rise of low fixture or fixtureless production, and of course, additive manufacturing. And there's a revolutionary wildcard technology from Tesla, and I'm going to talk about that in a moment. Robotics, well, robotics are fighting the fixture. Now, this FANUC application, this is typical of this current state-of-the-art in fixtureless fabrication and assembly. Now, the important takeaway here is that this system uses conventional off-the-shelf general-purpose robotics with relatively simple end-of-arm tooling, and it relies on the robot's intrinsic repeatability to hold parts in well-defined space for accurate assembly. Now, that repeatability usually scales inversely with the size of the working envelope, but we're seeing signs of integrated solutions that include things like machine vision and proximity detection with techniques like time-of-flight measurement. That's to enable accurate and precise feedback control positioning. Now, the implications for short or medium run manufacturing are significant. Motion control general purpose robotics, well, that's low cost and it's well understood. Removing fixturing costs could completely remove minimum volume requirements for short run production and significantly lower unit costs at the same time. At the same time, it could also reduce or eliminate project delays caused by the fabrication and qualification of production tooling, which is a major factor in large projects. Now, this fast turnaround capability is especially important because these robotic systems, as they exist now, well, they're expensive. They're as expensive as custom automation solutions for production. And complexity is also an issue. We're looking at multiple end effectors here, and they all have to move simultaneously and in coordination, which is a much more difficult problem to solve than just sequential operations with quick change in end-of-arm tooling, which you might see with a fixed fixtured solution. Now, from an assembly design consideration, applications like this have one major advantage, and that is they act as dynamic positioning systems rather than static fixtures. The ability to invert and rotate the part during work can allow the engineer to design assemblies of formerly difficult to reach attributes, and especially fasteners, splined and threaded parts and subassemblies. It's simply easier to get things to go together if we can rotate them and invert them in three-dimensional space. Now, what I think the exciting thing about this technology is its scalability. With work holding and tool holding moving from a hardware problem into software, coding skills and machine coding strategies translate well between the sort of tabletop collaborative robotics that we commonly see, for example, electronics or in pick and place, and the very large robots with ton scale payload capability that we're seeing in things like structural steel. Now, it's possible that we may create an entirely new type of engineer working in large assembly design and production that I'm calling the assembly coder. Now, we feel this is a short to medium term solution that the low code and no code robot programming technologies currently in development will make fixtureless technology accessible to large assembly engineers without extensive manufacturing experience or specific coding training. Now, the best part about this emerging technology is that the robots, controls, and end-of-arm tooling are all off-the-shelf products, and in some cases are even commodity items. So many fixtureless techniques, well, they can be developed as low-risk software-only projects using existing hardware. Well, robots are fighting the fixture, but they may be the fixture. If your world is designing the assemblies that make the assemblies, then end-of-arm tooling like this may be familiar. Now, completely replacing the fixture may not be the most efficient or cost-effective use of robotics for all applications. Mounting on the robot itself can offer several advantages. Now, the ability to rotate a fixtured part or assembly through multiple axes can give similar benefits to that fully fixtureless solution I just talked about with lower cost and complexity. Now, this kind of solution can also reduce or eliminate jigs by bringing the part or assembly to the punching, forming, or cutting operation rather than guiding a tool into the work. For volume production with larger assemblies, this strategy also opens up an interesting possibility, and that's the ability to pick up and hold multi-part assemblies for alignment or finishing work. For example, if your assembly needs a uniform flat surface across several parts, you've got a couple of options. One may be to design for precision assembly using piloted or doweled assemblies to hold everything in very, very close alignment. But it might be simpler and cheaper to coarse assemble first and then machine the assembly as a unit rather than design for precise assembly in the first place. Now, either way, this vision of the future, it'll combine the traditional role of the tooling engineer with the robot motion coder. The basic principles are going to be the same, but for the fixture as the end-of-arm tool, weight and inertial mass are major factors in repeatability and cycle time. So the need for rigidity with minimal weight means that traditional engineering methods for fixturing large assemblies involving things like conventional mild steel, they're going to have to be replaced with light alloys, composites, or maybe even highly skeletonized, additively manufactured components. I'll talk about more of the additive manufacturing aspect in a minute. Now, the other potential impacts for large assembly designers using fixtureless and hybrid solutions like these is potential use in manufacturing service businesses. Now, they're currently popular for the small part community using injection molding and additive. But as technologies like these allow the service bureaus to handle bigger and bigger assemblies, the design community can iterate or validate simulations without interrupting production workflows. Now, this may allow smaller design firms to work in the large assembly space and deliver functional prototypes as part of design validation services. Now, ironically, if technologies like these pull cost and lead time out of short-run production of large assemblies, that resulting decentralization of production may make the use of digital twin even more important. With a manufacturing facility in another country, state, county, the digital twin is the only way to cost-effectively engineer process improvements or design changes. And they kind of work synergistically with the hardware and digital twin supporting each other. Now, the IoT is a factor as well. If production tooling and the assemblies themselves are heavily instrumented, and all indications are this is going to be standard operating procedure very soon, process monitoring and quality assurance data can feed back into the digital twin and then further upstream into the assembly and tooling engineering processes. And the size or sophistication of the design engineering team may not matter. So it's a sort of a democratization of process improvement between big firms and small firms. Additive keeps growing. Now, there's no way to talk about engineering design or advanced manufacturing without talking about additive. Now, we track it closely, and the industry focus pre-COVID and throughout 2020 has been about additive as a true production technology as opposed to prototyping. Now, limitations on additive compared to machining or forming are sort of locked into the physics of the process itself. Fused deposition systems for resins and laser electron beam melting of metal powders present similar problems in that they're genuinely slow. They have to trade resolution and surface finish for speed. For parts of moderate size, the solution to the speed problem is simply to make the working envelope bigger and build multiple parts simultaneously. Now, commercial machines with working envelopes of a cubic meter and bigger are now commercially available, and that opens the door to additive as a part-making technology for large assemblies. This example in particular is a production operation using big rep equipment. Now, for both resin and metal applications, material selection is still relatively limited, but there's a growing list of copolymers, alloys, and even filled materials now available. On the plastic side, special purpose engineering resins are now available as the equipment manufacturers, as the machine makers, are co-developing materials with major resin and master batch houses. On the metal side, the trend toward larger working envelopes is similar, and some very large-scale units are now commercially available using technology derived from the welding industry. Now, the same rules apply, with speed defined by the metal deposition rate. Well, it's inversely proportional to the quality of the surface finish. Now, for some architectural applications, surface finishes are not a factor, or they might even be advantageous. But in most large assemblies, a post-build finishing step is a necessity, and it might be labor-intensive for complex and organic shapes. There's an exception in some heat exchanger engineering where that need to break laminar flow on cooling channel walls benefits from a rough surface texture. There's a design edge, free complexity. This EOS test part, this is typical of the kind of complex skeletonized design optimized parts that are possible with metal additive. While this is impossible to make cost effectively with a subtractive process like machining, it still has two machined mating surfaces, as you'll see, drilled through holes and tapped blind holes. Now, some post-processing by conventional machining is almost always part of additive designs intended for larger assemblies. Now, for a designer, it's tough to beat this from a strength-to-weight ratio perspective. And where high performance is the main criterion, well, this technology wins that cost to performance ratio contest too. And parts like this can be designed with almost unlimited complexity and internal structure with little added cost to make the part. But that complexity isn't quite free. The low-cost way to generate these optimized shapes is through generative design software. And for critical applications, performance simulation and simulation of the build are important too. And post-build processes are different for additive components compared to castings, weldments, or machine parts. Just holding a part like this for machining may require custom fixturing or specialized machining techniques to minimize distortion. Now, for designers who don't have the luxury of advanced simulation capability, it may be necessary to iterate, test, and break parts like this until the performance targets are achieved. For non-critical assemblies or assemblies that can be approximated with commodity materials, that's a viable strategy. And the ready availability of additive as a service vendors mean it's possible for an engineer to experiment with this technology without making that heavy commitment in hardware. Now, this image is typical of the kind of halo applications in additive manufacturing industry that they just love to showcase. But it's important to note that a lot of improvement can be had on the path between heavy machined and fabricated assemblies and really optimized structures like this. Even designers working without the benefit of advanced simulation, generative design, or finite element analysis, well, they can render design like this with simple, recursive, and triangulated reinforcement concepts. I mean, most of the weight and performance advantages are still there, and the additive can accommodate design changes easily after the fact. And this is worth investigating even if your design methodologies and your technologies are straightforward. Well, I talked about sort of the end of fixturing, but additive actually lets the fixturing community fight back. In an earlier slide, I commented on that future of fixtureless for fabrication. Although that might be the future for low volume, high mix operations with large structural assemblies, fixturing as we know it isn't going away anytime soon for many important applications. This year, we've noticed that fixturing is the most common application discussed by engineering teams at additive hardware makers. Although they won't say it directly, we believe this is a backdoor strategy to get mass production manufacturers comfortable with the technology and to get engineers experienced in path coding and design for additive. This image is of an open mold composite layup tool, and it gives a sense of the kind of scale that's currently possible with metal additive technology. An important advantage that we can exploit for large assembly work is the ability to use a smooth, polished, and hard-wearing top surface backed by a tougher but cheaper substrate. This can eliminate conventional post-machining surface treatments and plating, and the surface layer thickness can be tuned for the surface environment and the expected life of the tooling. Using the minimum amount of expensive material backed by commodity metals is always good engineering practice, but unofficially, several engineers working with this technology in the aerospace industry are talking about experiments in laser and electron beam metal powder parts with a composition gradient across the build. Now, for the gas turbine energy and process industries, this emerging technology is going to be very interesting because it can reduce or eliminate possible corrosion, stress concentration issues across a large assembly. More importantly, it can allow very tight control over thermal expansion. Now, we haven't yet seen commercial equipment that can deliver a variable CTE material across a build yet, but multi-material additive already exists, and we expect to see this in commercial use within about 5 years. There's a hybrid option. In today's world, for large assemblies, the surface finish speed and resolution limitations of metal additive are a deal breaker for many large assembly applications. Now, aerospace is a significant example where deployment of metal additive has been slowed by regulatory approval of the process, and so far it's been limited to smaller parts and assemblies. Hybrid manufacturing, combining metal additive and machining, can be used to avoid the drawbacks of both methods. It could deliver larger, more complex shapes with surface finishes, flatness, and concentricity that allows assembly as machined without those post-processing steps needed with additive-only technologies. This particular machine is from DMG Morisiki, and like others, it also has MRO applications. And this opens up some interesting design possibilities for tough, hard-wearing surfaces deposited on softer, more ductile substrates, or the exact opposite, with lower cost sort of friable surfaces that can be remanufactured in the same equipment that made the parts in the first place. The obvious applications for larger assemblies include things like bosses, lugs, brackets, flanges, and as hard-facing processes for assemblies in extreme environments. Valve components for the energy and process industries use this technology to good advantage now. Another advantage of a hybrid is G-code commonality. Operations designed for machine parts that need very specific, complex external attributes, well, they can get them without introducing additive as a new process into an existing workflow. This is a real advantage for this application for customers who need certification of their processes as well as their parts, and that institutional knowledge that they already have from machining that carries over directly. This is new, and this is particularly exciting. This is a new, very interesting application that we've been following with great interest. Disruption of existing technologies, well, it's a common theme for anything run by Elon Musk, and we've been following a very interesting development at Tesla's Brandenburg plant under construction near Berlin. Tesla's been looking at ways to simplify auto assembly, has announced a major project to mass produce the largest single die castings ever used in auto production. Now, at this time, Tesla's released very little specific detail about the system, and much of the photography you're seeing here is based on drone flights and nondescript press materials, but here's what we know right now. Tesla intends to produce vehicles for the European market using a radically different structure than current production. Their new chassis will consist of a floor-mounted battery pack, which is a stressed structural member of the chassis, connected to aluminum alloy die castings front and rear, with the three large assemblies forming a structural support for the body, suspension, driveline mounting, and of course providing the deformable structures necessary for collision energy attenuation. Now, this diagram shows an early iteration of that strategy. The previous design on the left used some 70 die cast and stamp components to form the rear subframe assembly on the Tesla Model 3. The Model Y, which is designed to have 75% parts commonality with the Model 3, well, it uses this huge light alloy die casting for dramatic reduction in part count, about 70–80%. Large-scale die casting has been used for decades for smaller suspension carriers, control arm assemblies, and notably for engine blocks, transmission differential housings, but it's never been attempted to make, in this application, to make assemblies this big. Now there's the large casting on the left. This is mounted on two standard 40-inch shipping pallets to give you a sense of scale. Now, high-pressure die casting of thin-wall parts of this size, it's a major engineering challenge. The tooling is obviously very large, and the Italian Idra press, pictured in the drone shot on the right, well, by necessity, it cycles slowly. Current cycle times are estimated at about 90 seconds. Now, to attain the desired million unit per year production rate, multiple machines are going to be used, and Musk has stated that he expects a 30% reduction in factory floor space due to the savings from part consolidation, a 20% reduction in labor costs in vehicle assembly. Now, this is going to work. Structurally, doing this front and back of a stressed member battery pack means passing the loads in a way that will have to take those bending moments assumed by the torque boxes of regular auto unit construction. Now, turning these three major structural parts into one rigid assembly presents a problem familiar to all designers of large assemblies, and that's the attach points. Now, it's unclear at this point whether those mating surfaces will be machined or as cast, or the types of fasteners used to build this roller skate. The rectangular extensions that resemble conventional frame arms in the picture on the left, well, they're part of the impact attenuation structure, and they're going to crumple with a minor impact. Now, obviously, replacing an entire front or rear clip after a minor bump impact is going to be a non-starter with the insurance industry. And as a result, Musk has announced service kits are going to involve cutting away damaged extensions and bolting on service kits. On top of all this, will still be a fairly conventional unit construction body shell, but it's unknown if that body in white is going to take some of these structural loads. Now, I expect it's going to contribute significantly to resisting torsional moments at least. From a design and engineering perspective, this is workable, but whether this will be lower in cost for production applications compared to highly automated assembly of conventional front and rear subframes, that is unknown at this point. But fabricated large assemblies have shown to be lower in cost in production applications compared to casting for large structural members, so I'm skeptical. But then a lot of people have been skeptical about successful Elon Musk blue sky projects, and if he pulls this off, this will create a rethink industry-wide of how large chassis are assembled. I briefly mentioned composites, and what about them? Well, so far it's been talked about metals and polymers for large parts and assemblies, especially with additive, but composites still in play. I mean, the two major beneficiaries of this technology are, of course, automotive and aerospace, but they're diverging on application development. Both industries are efficiency driven and both need high strength, lightweight structures. But in automotive, high strength, low alloy steels and specialty automotive grades of aluminum, they're still pulling substantial weight out of the product with conventional technologies. Now, for those ferrous alloys, the industry is still talking about down gauging. But the real secret that's little discussed is that it's FEA and advanced simulation on the design side that are allowing thinner and thinner sheet and less of it while making it work with controlled deformability and crash survivability, as well as reasonable noise, vibration, and harshness levels and chassis stiffness. It's a lot. Ford's 5-year billion-dollar project, the Novelis, for application-specific aluminum alloy for the F-150 program, that's pictured at the bottom, well, that's been an engineering and marketing success, and competitors are now using substantial amounts of aluminum in cab and box construction. And by introducing this first in pickups, Ford engineers still have that advantage of that ladder frame, removing much of the load path management duties of the body assemblies. Compared to two lightweight formable metals in steel and aluminum with wide commercial availability, we expect composites are going to stay small in automotive despite advances in automotive layout. For the aerospace airframe community, of course, it's a completely different story. 787, well, it's still the place to watch. It's almost a decade into that program, but Boeing's all-composite Dreamliner is still the subject of a lot of debate in the industry. Now, the design is without a doubt a major technical success, and airlines are reporting significant efficiency improvements in MRO and operating costs. But whether this project will achieve Boeing's profitability targets is still up in the air. The company uses a complex program accounting system that amortizes development costs over estimated production runs, which change over time. So later aircraft essentially pay for earlier aircraft. And as a result, Boeing's enthusiastic about selling newer, larger variants for higher prices with the bulk of the development cost already paid. Now, this illustration shows the other innovation in the program, that is that this is the most heavily outsourced major program in aviation history. And despite major assemblies coming from 4 continents, the program has been smooth running relative to the early predictions. Now, despite the technical success of this program, major competitors like Airbus are much more conservative, and they're sticking with light alloys and a moderate use of composites. Competing aircraft like the A350 extra wide body will have similar efficiency to the 787 with mixed construction of advanced light alloys. Now, critics of this program originally fell into 3 camps. The first argued that a fully composite airframe on this scale was too great a risk for the performance advantages that it would deliver. The second group argued that logistics would kill this program, that management of a supply chain across 4 continents, including subassemblies too big to fit in a 747, well, that would create problems impossible to solve. And the third group argued that managing the information flow across multiple engineering teams around the world would make the program unmanageable, regardless of the sophistication of ERP, PLM, or MES software. Now, from an engineering perspective, all 3 of these views were incorrect, and the product has had a very trouble-free service history relative to the amount of innovation it required. And Boeing approved this project after an analysis of engineering software at the state of the art in 2010. A decade later, integrated design and project management tools are available widely and at lower cost. So I find it surprising that many analysts predicted major issues across multiple industries with new product development today due to COVID. Now, this Dreamliner project is definitely an edge case. It's the most sophisticated project, a clean sheet design with many unknowns, and it was decentralized to an extent never before attempted. A decade ago, it worked across 4 continents. So today it's working at small and medium-sized engineering enterprises as well as multinationals in multiple industries. And of course, COVID's still there. Now, on the macro scale, Boeing proved that a multinational corporation with unlimited resources can decentralize design and manufacturing across the whole planet and still get large assemblies that fit and function well. Now, COVID-19 is creating a situation like this in miniature for thousands of engineering firms worldwide. The early consensus among firms we spoke with at engineering.com was that disruptions to the design process would be serious, with engineering teams unable to collaborate effectively while working at home. Now, many in the AR and VR community, they still feel that their technology is essential for collaborative remote work, and we hear similar claims from the 5G community on the network side. Despite this, we're not seeing a significant decrease in productivity or timeline slip in projects due to the isolating effect of COVID-19 on the design side for manufacturing-related industries. On the production side, the supply chain effects and suppressed consumer demand are though they're there, but so far we're not seeing reports that remote work has seriously impacted the design process, even with traditionally meeting-heavy efforts like change review and configuration control. And similarly, we're seeing no significant differences between the different engineering disciplines. Civil, mechanical, electrical, and the subspecialties, they appear to be much less affected by working remotely than we anticipated. So in summary, what have we learned? Well, all these results, they surprised us at engineering.com. Many of us who are older and have worked in the industry for years have assumed that face-to-face collaboration at formal meetings and at the water cooler, well, that they're integral parts of a creative and efficient design process. Now, at the other extreme, many generally younger engineers at the leading edge of technology, well, they're reporting that a new generation of AR and VR tech combined with much higher data rates would be needed for effective remote work. And so far, neither of these appear to be true. The human factors issue, however, is still unknown. We do know that some designers will enjoy the focus of working alone, and some need interaction with colleagues to stay creative. Most experts believe that we're solidly in the second wave of the COVID-19 pandemic, but with at least 2 vaccines currently showing promise, it's possible that by next summer, social distancing will be a memory. But the most common sentiment we're hearing across the engineering community is that the surprising effectiveness of the industry despite the lockdowns means that we'll likely never return to a fully staffed conventional design office environment. A hybrid model is likely with increased flexibility for employees, better morale, and paradoxically, a broadening of real-time collaboration between engineers, except now around the world. Now, we do combine this with new AR and VR tools and faster, more secure file handling systems. We expect the design engineers and their projects will be better off post-COVID than before. That's a lot. That's a vision for the future. But in the here and now, I'm going to turn this presentation over to Ben Weisenberger, who's going to tell you about some important strategies that you can apply today to large assembly engineering problems. And just a reminder, feel free to type your questions into the console in front of you now, and I'll present them to Ben in the Q&A portion at the end of his presentation. So Ben, over to you.
All right, thanks a lot, Jim. Appreciate it. As he said, my name is Ben Weisenberger. I'm an application engineer, part of the Solid Edge Global Technical Enablement team. With that, I kind of have a unique job of being able to help out with the development of Solid Edge, but also help market it and present to customers and prospects and get to see kind of what's going on in the industry and help kind of push the software in that direction. So what we're going to look at today, though, are a couple tips to kind of help us out dealing with some of these larger assemblies. How do we manage some of this data? How do we help with performance while handling the larger assemblies? So kind of some of the top things we're going to look at today: simplifying our components, paying attention to some of our drawings, how we can improve our models and take advantage of things like data management, and also optimizing our displays. So tip number one here, obviously, again, is to simplify your components. So one of the biggest impacts you can have on your assembly performance is to simplify your parts, especially if they're reused often. So for example, if your model includes a lot of hardware, you likely don't need all the little details, things like helical threads, markings on the head of a bolt, or small fillets. We don't need those to show up in the bill of materials or the drawing necessarily. Now, if showing the head shape and the body of the screw extruded to the correct depths are sufficient, then simplifying your part accordingly, will help out a lot. In many cases, modeling just the head of the screw or the bolt is enough representation of a standard part in a large assembly. Now, best-in-class CAD systems like Solid Edge also support occurrence property options, which allow us to call components such as bolts and fasteners from those upper-level assembly models. We can also consider doing analysis on our models and those needs when determining how much detail to show. Unless you are the bolt manufacturer, you likely don't need to do in-depth stress analysis on your bolts and your assembly. So very few companies really need to represent these parts with a high level of detail. Now, if you do interference checks and mass calculations at the subassembly level, you need to have a fairly accurate representation of your hardware, but you might be able to get away with a simplified representation of the hardware at the upper level. And remember that the computer must draw every edge that you create. And if you have hundreds or thousands of screws, a single extra edge on the screw means your computer has to redraw those extra 1,000 of edges. So the same sort of idea applies for electronic components on circuit boards, purchase motors, or pumps with a lot of detail. Now, when your assembly includes a subsystem that is either purchased or provided by a supplier, simplifying it to a single part file enables you to design in context without impeding performance. We're going to look at that next in a demo in just a minute of how we can quickly simplify purchased or larger subsystems down to a single file. We also need to define cohesive sets of parts, features and constraints as a single functional system and use this model in your actual design. So the time you spend up front will improve both your performance and your model accuracy. So here, as I mentioned, we're going to take a look at how we can actually simplify a model, in this case inside of Solid Edge. Here you see we have a grinder assembly. And what we want to do is simplify this down to one part file. That way we can reduce the file size when we take this into a larger assembly. What we're going to start with here is actually doing a clipping plane. I want to show you inside of that grinder, show you those internal components. And what I want to do when I simplify this is actually remove all of that intelligence on the inside. Maybe I want to share this assembly with a vendor or customer or something like that, and I don't want them to get my intellectual properties on the inside. So we're actually going to remove that information here in just a minute. Now what we're doing is we're switching into the simplify environment, and we're going to use a method here called the model simplification. Basically allows us to create generic or basic shapes to simplify the model. Or what we can do is we can go in and use one of our newer commands called auto simplify to help speed up that process. So here we'll go ahead and run the auto simplify command. We simply select the components that we want to include in the simplification process. So here I'm going to select the entire assembly. We can go ahead and accept that, and that will start to simplify it. Now, if we go back and we turn on that clipping plane that we set up just a minute ago, we can take a look inside of the assembly and see what happened. So initially, all that happened is the part files were boolean together into one solid model. But as I said before, I want to remove that internal intelligence. So we have an option up here on the command bar to actually do that automatically for us. And if we go ahead and select it, there we go. We can see it's now created this as a solid model. All of the internals have been stripped away, and we're stuck with now basically a shell of that assembly. What we can do then is we can save this assembly out to a part file and then share that again with vendors or customers, or use that upstream in a top-level assembly, again, to help reduce on performance and file usage in that larger assembly. So some really cool options that we have here inside of Solid Edge. Again, that is the auto simplify option. Now, another thing you want to do is make sure you pay attention to your drawings, and this often gets overlooked. Many times people don't look ahead to the drawings they're going to create of these larger assemblies. So the drawings have a big job when it comes to large assemblies. Multiple views of each assembly, including multiple parts and potentially cutaway, detail, or exploded views, mean that your CAD tool has to manage the display of a lot of different states. If we can avoid interferences where possible to keep our drawings performing well, then we want to make sure we do that. When your solid model has interferences, it causes display issues, which means that your system is spending more time calculating that bad display than it should. You want to make sure to check for interferences if you see anything amiss in your assembly views. Now, detail is great, and enthusiastic new 3D users sometimes get obsessed with how much detail they can create, but you can make bolts look very realistic right down to the grade markings on the head, rounded edges, textures, and highly detailed helical threads. But the problem with that is that it is costly in several different ways. First, all that detail takes a long time to create. Second, it takes a long time to display it every time you need to do so. And too much detail can have a critical impact when it comes to drawing performance. Drawings must calculate every edge and then decide if they're hidden, shown, grayed out, or dashed for every part every time it's shown. So excessive detail can make your model look more realistic, but it causes performance losses as a result. So this sounds simple enough, improve your model, right? But this is a good way to actually, again, help deal with these large assemblies and make them perform faster. So some things we can do in the assembly, some things we do in the assembly do take up more computational resources than others. Things like assembly features. So for example, they require the assembly to make sure that the parts are updated. We then bring those parts into the assembly, position those parts, and then add the feature to the position parts with potential differences between the part occurrences. So every time you open this assembly with assembly features, it has to do that every time, and that can really add up to a performance hit. Another thing is inter-part relationships. And they're also very costly for some of the same reasons. So this is one of the reasons why synchronous parts specific to Solid Edge and assemblies are recommended for better performing assemblies. You can create relationships between parts in an assembly only when needed without associative links. If you do need the link, you can consider freezing that when you're done working with an area of assembly to help further improve performance. Another big issue with assemblies and models is issues with relationships and failed relationships. So we introduced a tool a couple versions ago in Solid Edge called the Assembly Relationship Manager. What this allows us to do is view all of the relationships placed on an assembly in one easy to use display here. So we're going through our dialog here, and we can see all the relationships either by the separate components or by the different relationship type. Then what we can do is filter down that list of relationships, in this case to see some relationships with missing geometry. That saves us time from having to hunt through every single component in the assembly to find these issues. We can quickly find them in one easy to use dialog, and then we can come in here and use some options to try to repair those relationships. In this case, we've simply suppressed them to kind of get over the issue temporarily, But if we go back in and unsuppress one of them, we can interrogate what the issue actually is. We can see that it's missing some geometry. So one of the faces that was defined to do this offset, do this planar align relationship, one of those faces has been changed or is now missing in the relationship itself. So by using this assembly relationship manager, we can easily go in and edit that relationship simply by double clicking on it. And it takes us to the exact part of the relationship that is missing the geometry. In this case, on this cylindrical shaft part through the middle there, we're missing what face we wanted to do the planar align to. So simply clicking a face fixes that relationship and solves our issue. So again, another quick and easy to use tool there inside of Solid Edge to help us improve our models, clean up those broken relationships or missing geometry relationships, quick and easy there. Now, another good solution is using PDM. So another common source of performance problem comes from referencing files stored across a distributed network. And that couldn't be more true here than it is now working from home. Everyone trying to access files either at the office, across the network can be extremely difficult. So some of the best ways to avoid those performance problems due to a networked file is to use a product data management system or PDM system. So these PDM systems can be more cost effective than many companies realize and can result in substantial performance gains. So while the PDM vault is in a central location, when you check your files out to use them, they are copied down to your local machine and a cached version locally. The PDM system can accomplish this in a way that doesn't cause problems with duplication, overwriting, or permissions. So this gives you the advantage of working on shared files without the normal disadvantages of sharing files across the network. PDM also helps you avoid complicated rules aimed at avoiding overwriting other users' changes, revision control on solid models, and tons of additional file management problems. So if you're concerned about your assembly performance, a simple PDM tool should be a priority. Now, Siemens PLM software provides a scalable set of data management solutions that meet the varying needs of small to large manufacturing organizations who may design simple, or in this case, very complex products. So these Solid Edge CAD data management solutions enable you to rapidly take key actions to improve your product development performance. We can secure and control our product data and processes, enable rapid retrieval of all the correct information to improve efficiency and facilitate reuse. If we need to, we can share product information and collaborate with downstream functions such as manufacturing to improve quality. And we can also follow industry best practice workflows for engineering change and release to manufacturing. So some of those solutions range from an integrated data management capabilities that's free with Solid Edge to the comprehensive CAD data management and product lifecycle management capabilities of Teamcenter. Now, a newer solution I want to talk about is Teamcenter Share, and this is not CAD specific. Teamcenter Share is available for any CAD system out there today. We have the ability to view, measure, and mark up any CAD on any device. In this example we see here, we have a sewing machine uploaded to the cloud to Teamcenter Share, and in this case, we're creating a markup on that assembly saying we need to make some sort of a change. What we can do then is we can synchronize that product from the cloud down to our local machine. So this is similar to something like Dropbox or Google Drive, but it's CAD specific. We also have integration inside of Solid Edge. So this is unique. We can only do this inside of Solid Edge today. But again, uploading and saving those files and viewing them and marking up is available on any CAD device. But some of the great things about having this integrated in Solid Edge is we can measure any CAD file that we have uploaded without actually having to open it inside of the CAD system. If we want to open up one of the files, we can, and then we can also do our view and markup right here inside of the assembly document. In this case, we see that markup that was created earlier, maybe by a manager, saying we need to make a change to one of our brackets. If we use that integrated data management solution with Solid Edge, we can also ensure that files don't get overwritten. If we have a coworker working from home on a different portion of this assembly, it ensures that whatever project they're working on will not be overwritten by what I'm doing here. Those files are checked out to each user separately without being able to overwrite one another. Once we've made our change, we can then go in and add some additional feedback right here again inside of Solid Edge, saying, hey, we've deleted those holes. We've made that edit, it's now complete. and that can be shared back then to our manager to let him know that the work has been done. We also have the capability then to collaborate and share. Again, another big useful option right now in today's world is being able to share these projects easily. So having this uploaded on the cloud, I can easily enter in a user I want to share this with, give them full view markup download capabilities, or simply just allow them to view that model. And then also integrated with Teamcenter Share is the AR capabilities that we see here. We can take any of those models that we've uploaded, again, from any CAD system, not specific to just Solid Edge, and we can view those models in AR so we get a real world representation of what that model is actually going to look like. So some really great stuff there that we can use to manage our files easily. Finally, my last tip here is to optimize our display. So the visual effects inside of a display, they can help convey an accurate look and feel and create a realistic look to communicate with partners, customers, and your shop floor. But in your upper level assemblies where the system performance becomes an issue, you want to consider that trade-off between the parts that look cool and faster modeling capabilities. To optimize our upper level assembly performance, we want to do things like turn off reflections, turn off drop shadows, turn off cast shadows, and even silhouettes. One of the great things that was added in the last version of Solid Edge 2020, is a large assembly performance option. It's a one-click button that you can hit that will do all of these options for you automatically to help speed up that performance. So when you need that extra memory storage or performance boost to rotate your large assembly around, you simply hit that button. It turns these options on and off and gets you into a quicker, larger assembly performance mode. You can do your work, and then when you want it to look good again, you simply toggle off the option and you're back to with that good looking assembly again. So again, keep that in mind. Think about what's on your screen and what kind of processing has to be done to show that information, and make sure you're doing the appropriate thing for your machine and the type of assemblies that you're working with. So just want to throw my contact information up there. Hopefully you guys got some good tips from that. If you have any questions that we don't answer today, feel free to reach out to myself and I'll be happy to get back with you and talk through some of this again and help out with some other tips and tricks. I also wanted to let you know that you can go out and download a free trial of Solid Edge today. I've included the link here, but we'll also include the link in a follow-up email after this webinar. But again, it's a free download of Solid Edge. You can go grab that trial, play around with some of the things I talked about today, and experience it for yourself. We also have a link there to learn more about assembly modeling and data management with Solid Edge. So please visit that as well, and it's full of a lot of good information. A lot of the things that I presented today are out there as well.
Ben Weisenberger, Senior Application Engineer, Solid Edge Global Technical Enablement with Siemens Digital Industries Software. Thanks for a fascinating presentation. I'm Jim Anderton, Director of Content for Multimedia here at engineering.com. Thanks everyone for attending, and thanks to Siemens for sponsoring today's webinar. Goodbye.